space is often imagined as a silent, dark emptiness. But in reality, it is a universe of extremes. Some places burn with temperatures hotter than millions of degrees, while others exist in conditions so cold that almost nothing can move. On Earth, the coldest temperature ever recorded reached about -89 degrees Celsius in Antarctica. Yet, compared to the universe, that temperature is almost warm, because somewhere in the depths of space exists a region colder than anything ever found on our planet, a place where the temperature drops to nearly absolute zero, the coldest known location in the entire universe. Tonight, we explore this frozen cosmic mystery and how such an unbelievably cold place can exist in a universe filled with stars. When we think about cold, most of us imagine winter. We picture snow-covered landscapes, frozen lakes, and the biting wind of extremely cold places on Earth. Perhaps the first location that comes to mind is Antarctica, the coldest continent on our planet. In 1983, scientists recorded the coldest natural temperature ever measured on Earth at the Vostok Station in Antarctica. The temperature dropped to around -89 degrees Celsius. For humans, that level of cold is almost unimaginable. The air becomes painful to breathe. Skin can freeze in minutes. Machinery struggles to operate. Even metal becomes brittle in such conditions. Yet in the scale of the universe, this temperature is not particularly cold. In fact, compared to some places in space, it would almost feel warm. To understand why, we need to look at temperature in a different way, the way physicists understand it. Temperature is not just about how something feels. It is actually a measure of how fast atoms and molecules are moving. Everything in the universe is made of tiny particles called atoms. These atoms are constantly moving, vibrating, and interacting with one another. When atoms move quickly, the temperature of a substance increases. When their motion slows down, the temperature decreases. In other words, heat is simply the motion of particles. The colder something becomes, the slower its atoms move. Eventually, physicists discovered that there must be a limit to how slow atomic motion can become. There must be a lowest possible temperature, where particles cannot slow down any further. This temperature is known as absolute zero. Absolute zero is the coldest temperature theoretically possible in the universe. It occurs at -273.15 degrees Celsius, or 0 Kelvin on the Kelvin temperature scale used in physics. At this temperature, atoms are at their lowest possible energy state. Their motion is reduced to almost nothing. Absolute zero represents the ultimate limit of cold, but reaching absolute zero is extremely difficult. In fact, scientists believe it may be impossible to reach it perfectly in nature. No natural process has ever been observed to bring matter exactly to this temperature. However, certain places in the universe come surprisingly close. Before scientists began studying these regions, they assumed that the coldest places in the universe would simply be the empty spaces between stars. After all, space is dark and mostly empty. Without nearby stars to provide warmth, it seems logical that the temperature there would be incredibly low. And in many ways, that assumption is correct. The vast regions between stars, known as interstellar space, are extremely cold. But even interstellar space has a temperature. This temperature comes from something called the cosmic microwave background, often shortened to the CMB. The cosmic microwave background is a faint glow of radiation that fills the entire universe. It is the leftover heat from the Big Bang, the massive explosion that created the universe nearly 13.8 billion years ago. In the early universe, everything was extremely hot and dense, but as the universe expanded over billions of years, it cooled down. The radiation left behind from that early period continues to travel through space even today. That ancient radiation sets a baseline temperature for the entire universe. Today, the temperature of the cosmic microwave background is about 2.7 Kelvin, which is approximately minus 270 degrees Celsius. This means that even the emptiest regions of space are not completely cold. They are filled with this faint background radiation, which keeps the temperature slightly above absolute zero. For a long time, scientists assumed that nothing in nature could be colder than this cosmic background temperature. After all, the entire universe is bathed in this radiation. Yet, in the late 20th century, astronomers made a discovery that challenged this assumption. They found a place in space that was even colder than the background temperature of the universe itself. A place where gas had cooled to temperatures almost reaching absolute zero. This discovery shocked astronomers, because according to earlier theories, such extreme cold should not have been possible. The object responsible for this discovery is known as the Boomerang Nebula. Located about 5,000 light-years from Earth in the constellation Centaurus, the Boomerang Nebula is currently considered the coldest natural place ever observed in the universe. The temperature inside this strange cosmic cloud drops to about 1 Kelvin, or roughly minus 272 degrees Celsius. That makes it even colder than the surrounding space. But how can something be colder than space itself? The answer lies in the unique physical processes occurring inside this nebula. To understand what is happening there, we first need to understand what a nebula actually is. A nebula is a large cloud of gas and dust floating in space. Nebulae come in many forms. Some are regions where new stars are being born. Others are the remains of dying stars that have expelled their outer layers into space. The Boomerang Nebula belongs to the second category. It is what astronomers call a pre-planetary nebula, a short transitional phase in the life of a dying star. At the center of the Boomerang Nebula lies a star that was once similar to our Sun. After billions of years of nuclear fusion, the star began to run out of fuel. As it aged, its outer layers expanded and eventually began to escape into space. When a star enters this phase, it can eject enormous amounts of gas outward at incredible speeds. In the case of the Boomerang Nebula, this gas is expanding outward at more than 160 kilometers per second. This extremely rapid expansion is the key to the nebula's extraordinary cold temperature. When gas expands quickly, it cools. This is a principle known as adiabatic cooling. It is the same basic effect that occurs when gas escapes from a compressed container or when air rapidly expands in the atmosphere. As the gas spreads out into a larger volume, its particles lose energy and their motion slows down. The result is a dramatic drop in temperature. Inside the Boomerang Nebula, the gas is expanding so rapidly that it cools faster than it can absorb heat from the surrounding universe. This allows the nebula to reach temperatures lower than the cosmic microwave background itself. In other words, the Boomerang Nebula is essentially creating its own extreme refrigeration system on a cosmic scale. The expanding gas acts like a gigantic natural freezer in space. Because of this unusual process, the nebula has become the coldest natural environment ever discovered. Astronomers first confirmed this astonishing temperature using radio telescopes capable of detecting the behavior of molecules within the nebula. By studying the way molecules absorb and emit radiation, scientists were able to determine the temperature of the gas. The results were remarkable. No other natural object in the universe had ever been observed to reach such extreme cold. But the Boomerang Nebula is not only famous for its temperature. Its structure is also visually striking. Images captured by telescopes reveal a beautiful, symmetrical shape resembling the wings of a butterfly or the curve of a boomerang, which is how it received its name. Two massive lobes of gas extend outward from the central star, forming an hourglass-like structure. These lobes are composed of gas that has been violently expelled from the dying star at the center. Over time, this gas will continue expanding into space, eventually merging with the surrounding interstellar medium. Eventually, the central star will shed even more of its outer layers, forming what astronomers call a planetary nebula. In this later stage, the star's exposed core will heat the surrounding gas, causing it to glow brightly. Ironically, the coldest place in the universe will not remain cold forever. As the star continues its evolution, the nebula will eventually warm and shine as one of the many glowing clouds scattered throughout our galaxy. But for now, the Boomerang Nebula remains a remarkable reminder of how extreme the universe can be, a place where gas expanding through the darkness of space has created temperatures colder than the cosmic background itself, a place where nature has pushed the limits of cold almost as far as physics allows. And this discovery raises an even more intriguing question. If such extreme temperatures can exist naturally in space, what other extraordinary environments might still be waiting to be discovered in the universe? That is what we will explore in the next part. The coldest place ever discovered. When astronomers first studied the Boomerang Nebula in detail, they realized they were looking at something extraordinary. Most nebulae in the universe are cold compared to stars, but they are not that cold. Typical nebulae have temperatures of tens or even hundreds of degrees above absolute zero. But the Boomerang Nebula was different. Measurements showed that its temperature dropped to about 1 Kelvin, which is roughly minus 272 degrees Celsius. That is only 1 degree above absolute zero. To put that into perspective, the background temperature of the universe, created by the cosmic microwave background, is about 2.7 Kelvin. This means the Boomerang Nebula is actually colder than the natural temperature of space itself. For astronomers, this was a shocking discovery. Until then, scientists believed that nothing in nature could cool below the temperature set by the cosmic background radiation. Yet somehow, this strange cloud of gas had managed to do exactly that. The key to this mystery lies in the way the nebula is expanding. At the center of the Boomerang Nebula is a dying star that is rapidly ejecting gas into space. This gas forms two giant lobes that extend outward from the central star, creating the nebula's distinctive shape. But the speed of this expansion is what makes the nebula unique. The gas is rushing outward at incredible velocities, more than 160 kilometers per second. When gas expands that quickly, its particles spread out and lose energy. This process is known as adiabatic expansion, and it causes the temperature of the gas to drop dramatically. It is similar to what happens when compressed air escapes from a container. If you release air from a pressurized can, the gas expands rapidly and becomes cold. Sometimes the container itself becomes covered in frost. In the Boomerang Nebula, a similar process is happening on a cosmic scale. The expanding gas cools so rapidly that it reaches temperatures lower than the surrounding universe. In other words, the nebula is acting like a gigantic natural refrigerator floating in space. The discovery of this extreme cold was confirmed using powerful radio telescopes. Astronomers studied the way molecules within the nebula absorb and emit radiation. These molecular signals allowed scientists to determine the temperature of the gas with remarkable precision. The results were unmistakable. The Boomerang Nebula was colder than anything ever observed in nature. But temperature is only one of the nebula's remarkable features. Its shape is equally fascinating. Images captured by large telescopes reveal a beautiful structure that resembles a pair of glowing wings extending outward from the central star. This shape gives the nebula its name. The expanding gas forms two enormous lobes that stretch across space in opposite directions, creating a structure that resembles a boomerang or butterfly. Inside these lobes, the gas continues to cool as it expands further into space. Astronomers believe that the central star may once have been similar in size and mass to our Sun. But as it reached the end of its life, the star began to shed its outer layers in a violent outflow of gas. This phase occurs late in the life of many stars. After billions of years of burning hydrogen in their cores, stars eventually exhaust their fuel. When this happens, their outer layers become unstable and can be expelled into space. The Boomerang Nebula represents a short but dramatic moment in this process. Eventually, the star at its center will lose most of its outer material and leave behind a dense core known as a white dwarf. As this happens, the surrounding gas will become heated and illuminated by intense radiation from the exposed core. Ironically, the coldest place in the universe will eventually transform into a glowing cloud of hot gas. But for now, the Boomerang Nebula remains a unique cosmic phenomenon. No other natural object discovered so far has reached such extreme temperatures, and its existence reminds astronomers that the universe is capable of producing environments far more extreme than we once imagined. A place colder than the background temperature of the universe itself. A place where the laws of physics create conditions that seem almost impossible. And this raises another fascinating question. If nature can produce temperatures this close to absolute zero, what happens when humans try to reach even colder temperatures here on Earth? In the next part, we will explore how scientists in laboratories have managed to create temperatures even closer to absolute zero, colder than anything found naturally in the universe, colder than space. On Earth, the Boomerang Nebula may be the coldest natural place in the universe. But surprisingly, it is not the coldest place ever created, because here on Earth, scientists have managed to go even further. Inside highly controlled laboratories, researchers have pushed temperatures closer to absolute zero than anything found in nature. These experiments take place in specialized environments, using advanced techniques designed to slow down atomic motion as much as possible. And the results are extraordinary. In some cases, scientists have reached temperatures as low as a few billionths of a degree above absolute zero. That is colder than the Boomerang Nebula, colder than the background temperature of the universe, colder than almost anything that can naturally exist. But how is this even possible? To understand this, we need to return to a key idea. Temperature is simply the motion of atoms. So if we want to make something colder, we need to slow those atoms down. The challenge is that atoms are constantly moving, even in extremely cold environments. At room temperature, atoms move incredibly fast, thousands of meters per second. Even at very low temperatures, they still retain some motion. To reduce that motion further, scientists use an incredible tool. They use lasers. At first, this might sound strange. Lasers are usually associated with heat and energy. But under the right conditions, lasers can actually be used to cool atoms down. This technique is known as laser cooling. Here is how it works. Scientists shine carefully tuned laser beams at a group of atoms. These lasers are designed so that when atoms move toward the light, they absorb photons in a way that slows them down. Each time an atom absorbs and re-emits a photon, it loses a tiny amount of momentum. Over time, repeated interactions with the laser light gradually reduce the atom's motion. The atoms begin to slow down, and as they slow down, their temperature drops. Using this method, scientists can cool atoms to extremely low temperatures, often just millionths or even billionths of a degree above absolute zero. But the process does not stop there. To go even further, researchers use another technique called evaporative cooling. In this method, the highest energy atoms, the ones still moving relatively fast, are allowed to escape from the system. As these faster atoms leave, the remaining atoms have lower average energy. This causes the overall temperature of the system to drop even further. By combining laser cooling and evaporative cooling, scientists can create conditions that push matter to the very limits of physics. At these temperatures, something remarkable happens. Matter begins to behave in ways that are completely different from what we see in everyday life. One of the most fascinating states created under these conditions is known as a Bose-Einstein condensate. In this state, atoms become so cold that they begin to act as a single quantum object. Instead of behaving like individual particles, they merge into a unified wave-like state. In a Bose-Einstein condensate, the distinction between individual atoms disappears. They move together as if they are one entity. This is not something we ever experience in our normal world. It is a completely different phase of matter, governed by the strange rules of quantum mechanics. In this ultra-cold state, scientists can observe phenomena that are impossible to study at higher temperatures. For example, superfluidity, where a liquid can flow without any resistance, or quantum interference, where matter behaves like waves instead of particles. These experiments are not just scientific curiosities. They help researchers understand the fundamental laws of physics. They also have practical applications. Ultra-cold atoms are used in the development of extremely precise atomic clocks, which are essential for technologies like GPS. They are also being studied for potential use in quantum computers, which could revolutionize computing in the future. But despite these incredible achievements, there's still one limit that scientists cannot cross: absolute zero itself. No matter how advanced the technology becomes, reaching exactly 0 Kelvin remains impossible. There is always a tiny amount of residual motion that cannot be completely removed. This is a fundamental rule of physics. Yet, the fact that humans have come so close is remarkable. In laboratories on Earth, we have created conditions colder than any natural place in the universe, colder than the Boomerang Nebula, colder than the cosmic background radiation, and still, the universe continues to challenge us. Because while we can create extreme cold in controlled environments, nature itself has already produced places that push the limits of what we thought was possible. From distant nebulae to ultra-cold laboratories, the concept of temperature reveals just how strange and fascinating the universe can be. And as we continue exploring, one question remains. If we can reach such extremes of cold, what else might be possible in the depths of space? What happens at extreme cold? As temperatures drop closer and closer to absolute zero, the universe begins to behave in ways that seem almost unreal. At normal temperatures, the world around us feels solid and predictable. Objects behave in ways we understand. Matter has familiar properties. Solids stay solid, liquids flow, and gases expand. But at extremely low temperatures, these rules begin to break down. To understand why, we need to remember something important. Everything around us is made of atoms, and these atoms are constantly moving. At higher temperatures, atoms move rapidly, colliding with each other and creating the energy we perceive as heat. But as temperature decreases, this motion slows down, and as it slows, the strange nature of physics begins to reveal itself. At extremely low temperatures, matter enters the realm of quantum mechanics. In this regime, particles no longer behave like tiny solid objects. Instead, they begin to act like waves. And this is where things start to get truly strange. One of the most fascinating phenomena that appears at ultra-low temperatures is superfluidity. A superfluid is a state of matter in which a liquid can flow without any resistance. Imagine pouring a liquid into a container. Normally, friction would slow it down, but a superfluid can continue moving indefinitely without losing energy. It can even climb up the walls of a container and escape, defying our everyday expectations of how liquids should behave. This behavior has been observed in liquid helium when it is cooled to extremely low temperatures. Another strange effect is superconductivity. In this state, certain materials can conduct electricity with zero resistance. Under normal conditions, electrical currents lose energy as they move through a material, generating heat. But in a superconductor, electrons can flow freely without losing any energy at all. This allows currents to persist indefinitely. Superconductors have already found practical uses in technologies like MRI machines and particle accelerators. But at even lower temperatures, matter begins to do something even more unusual. It begins to lose its individuality. In conditions close to absolute zero, atoms can form what scientists call a Bose-Einstein condensate. In this state, atoms become so cold that they occupy the same quantum state. Instead of behaving as separate particles, they merge into a single unified system. It is as if thousands, or even millions of atoms begin acting as one. In this state, the normal boundaries between particles disappear. Matter behaves more like a wave than a collection of individual atoms. This is one of the strangest forms of matter ever observed. It exists only under extremely controlled conditions, and only for very short periods of time, yet it provides a window into the fundamental nature of reality. Another fascinating consequence of extreme cold is the slowing of chemical reactions. At very low temperatures, reactions that normally occur quickly can slow down dramatically, or even stop entirely. This is because chemical reactions depend on the motion of atoms and molecules. When that motion is reduced, reactions become less likely to occur. In the coldest regions of space, this effect can lead to the preservation of molecules over incredibly long periods of time. Complex molecules can survive in interstellar clouds for millions of years, waiting for the right conditions to trigger new chemical activity. Extreme cold also affects light and radiation. At low temperatures, objects emit less thermal radiation. This makes them more difficult to detect. In fact, some of the coldest objects in the universe are nearly invisible because they emit so little energy. This is one reason why detecting objects like the Boomerang Nebula, or potentially even colder regions, requires highly sensitive instruments. But perhaps the most important thing to understand about extreme cold is that it reveals the limits of our classical understanding of physics. At everyday temperatures, the laws of physics appear simple and predictable. But as we approach absolute zero, the universe behaves in ways that challenge our intuition. Particles act like waves. Matter can flow without resistance. Electric currents can persist forever, and atoms can merge into a single quantum state. These phenomena are not just strange curiosities, they are fundamental aspects of how the universe works, and studying them allows scientists to explore the deepest levels of physical reality. The closer we get to absolute zero, the more we uncover about the hidden nature of the universe. And yet, despite everything we have learned, one mystery remains. Why does the universe allow such extreme conditions to exist at all? Why can matter behave in such strange ways when it becomes cold enough? And what other unknown phenomena might still be waiting to be discovered in the coldest corners of space? These questions take us deeper into the nature of the universe itself, and they remind us that even something as simple as temperature can reveal profound truths about reality. Cold regions beyond the Boomerang Nebula. The Boomerang Nebula is often called the coldest natural place in the universe, but it is not the only cold region in space. In fact, extreme cold is far more common in the universe than heat, especially in the vast, dark regions between stars. Most of the universe is not filled with blazing stars or glowing galaxies. It is filled with emptiness, and in that emptiness, temperatures can drop to incredibly low levels. However, not all cold places are the same. Some regions are cold simply because they are far from stars. Others are cold because of unique physical processes, like the rapid expansion seen in the Boomerang Nebula. To understand the full picture, we need to explore other cold environments in the universe. One of the most important of these is interstellar space, the space between stars. At first glance, it might seem like the coldest possible place. There are no nearby heat sources, no sunlight, and almost no matter. Yet even here, the temperature is not zero. As we discussed earlier, the universe is filled with the cosmic microwave background, which keeps the temperature of interstellar space at about 2.7 Kelvin. That is extremely cold, about minus 270 degrees Celsius, but still warmer than the Boomerang Nebula. This means that even the emptiest regions of space are not completely frozen. Another type of cold environment can be found in molecular clouds. These are dense regions of gas and dust where new stars are born. Because they are so dense, they can block out external radiation, allowing their interiors to cool down significantly. Some molecular clouds can reach temperatures as low as 10 Kelvin. That is still warmer than the Boomerang Nebula, but cold enough for interesting chemistry to occur. In these clouds, atoms combine to form molecules including water, carbon monoxide, and even more complex organic compounds. These molecules can remain stable for long periods of time due to the low temperatures. In a sense, molecular clouds act like cosmic laboratories, where the building blocks of stars, and possibly life, begin to form. Another fascinating cold environment exists much closer to home. objects in the outer solar system, such as Pluto, Triton, and distant Kuiper Belt objects, experience extremely low temperatures due to their distance from the Sun. On Pluto, surface temperatures can drop to around minus 230 degrees Celsius. That is cold enough for nitrogen and methane to freeze into solid ice. Yet even Pluto is still warmer than many regions of deep space. This is because it still receives some energy from the Sun, even at its great distance. Beyond Pluto, in the far reaches of the solar system, temperatures continue to drop. In the Kuiper Belt, objects exist in near darkness, illuminated only by faint sunlight. Farther still lies the Oort cloud, a distant region that may extend tens of thousands of astronomical units from the Sun. Here, the Sun appears as nothing more than a bright star. Temperatures in this region are expected to be close to the background temperature of the universe. Yet even here, the temperature does not fall below the cosmic background level. This is what makes the Boomerang Nebula so unique. It is one of the few known places where natural processes have managed to push temperatures below that universal baseline. But the story of cold in the universe does not end there. There are also exoplanets, planets orbiting other stars, that exist in extremely cold environments. Some of these planets orbit very far from their stars, receiving almost no heat. Others are rogue planets, worlds that have been ejected from their original star systems and now drift through interstellar space. These rogue planets can become incredibly cold, especially if they have no internal heat sources. Without a star to warm them, their surfaces may freeze to temperatures close to the cosmic background. However, even these worlds are unlikely to be colder than the Boomerang Nebula. Because without a mechanism like rapid gas expansion, it is difficult for natural systems to cool below the background temperature of the universe. This highlights an important idea. Extreme cold in the universe is not just about distance from heat sources. It is also about how energy is lost. In most cases, objects in space slowly radiate heat away until they reach equilibrium with the cosmic microwave background. But in rare cases, like the Boomerang Nebula, energy is lost faster than it can be replaced. This creates temperatures that go beyond what we normally expect. And it shows us that even in the vast emptiness of space, the laws of physics can produce surprising and unexpected results. The universe is not just a place of extremes, it is a place of exceptions. Places where normal rules seem to be pushed to their limits. Places where matter behaves in ways that challenge our understanding. And somewhere out there, beyond what we have already discovered, there may be even colder regions waiting to be found. Regions that push the limits of temperature even further. Because in the universe, every answer often leads to a new question, and the search for the coldest place may not be over yet. Could anything be colder? After discovering places like the Boomerang Nebula, scientists began asking a deeper question. Have we truly found the coldest place in the universe? Or could something even colder exist? At first, the answer seems simple. The temperature of the universe is set by the cosmic microwave background, about 2.7 Kelvin. And only very special conditions, like the rapid expansion of gas, can push temperatures below that level. The Boomerang Nebula does exactly that. So it might seem like we have already reached the limit of natural cold. But the universe has a way of surprising us. One possibility scientists consider is that there may be other objects similar to the Boomerang Nebula, or even more extreme. The Boomerang Nebula is just one example of a dying star ejecting gas at high speed. there could be other stars undergoing similar processes, perhaps even more violently. If gas expands faster, it can cool even more. That means there might be regions in the universe that are colder than anything we have observed so far, simply because we have not discovered them yet. Another possibility lies in the early universe. Right after the Big Bang, the universe was extremely hot. But as it expanded, it cooled. Over billions of years, it has continued to cool down. In the far future, trillions of years from now, the universe will be much colder than it is today. Stars will burn out, galaxies will drift apart, and the universe will approach a state where almost no heat remains. This future scenario is sometimes called the heat death of the universe. In that state, the temperature of the universe will get closer and closer to absolute zero. Everything will become cold, dark, and inactive. In a way, the coldest place in the universe might not exist yet. It might be something that only appears in the distant future. There are also more exotic ideas. Some scientists have proposed that certain regions near black holes could experience unusual temperature effects. Black holes themselves are often associated with extreme heat due to the energy released by matter falling into them. But far from the event horizon, in isolated conditions, space around black holes can be extremely cold. In fact, black holes themselves have a temperature, something known as Hawking radiation. For large black holes, this temperature is incredibly low, much lower than the temperature of the cosmic microwave background. This means that, in theory, an isolated black hole could be one of the coldest objects in the universe. However, detecting such temperatures is extremely difficult. The radiation is so weak that it has never been directly observed. Still, it suggests that the universe may contain forms of cold that we do not yet fully understand. Another fascinating idea involves dark matter. Dark matter makes up a large portion of the universe, yet we cannot see it directly. We do not know exactly what it is made of. But if dark matter interacts very weakly with normal matter, it could exist at extremely low temperatures. Some theories suggest that dark matter particles might have very little motion, meaning they could be colder than ordinary matter. But because we cannot directly observe dark matter, this remains purely theoretical. Even within our own solar system, there may be cold environments we have not yet explored in detail. Deep beneath the surfaces of distant icy moons, or in shadowed regions where sunlight never reaches, temperatures could drop to extremely low levels. Yet, none of these environments are expected to reach the extremes seen in places like the Boomerang Nebula. What all of these ideas have in common is one important truth. We do not yet know everything about the universe. Every time scientists discover something new, it often leads to even more questions. The Boomerang Nebula was once thought impossible, yet it exists. And that means other unexpected phenomena may also exist. Somewhere in the vast darkness of space, there could be regions colder than anything we have observed so far. Or perhaps the coldest places are not physical locations at all, but future states of the universe that we have not yet reached. The search for the coldest place is not just about temperature. It is about understanding the limits of nature. How far can the laws of physics be pushed? How slow can matter move? How close can we get to absolute zero? These questions take us to the very edge of our understanding, and they remind us that even something as simple as cold can lead to some of the deepest mysteries in the universe. Because in the end, the coldest place in the universe may not just be a location, it may be a clue, a clue that points us toward a deeper understanding of reality itself. The physics behind extreme cold. To truly understand the coldest places in the universe, we need to look deeper, not just at where these places are, but at why they become so cold in the first place. Because extreme cold is not random. It follows the laws of physics with incredible precision. At its core, temperature is a measure of energy. More specifically, it is the average kinetic energy of particles, how much motion atoms and molecules have. When particles move fast, the temperature is high. When they slow down, the temperature drops. So the question becomes, how does the universe remove energy from matter? There are several key processes that can cause something to cool. The most common is radiation. Every object in the universe emits energy in the form of electromagnetic radiation. Even you, right now, are radiating heat. In space, where there is no atmosphere to trap energy, objects can lose heat very efficiently by radiating it away. Over time, they cool down. This is why objects in space, far from stars, tend to become extremely cold. But radiation alone usually brings objects down to a certain limit, the temperature of the cosmic microwave background. To go even colder, something more extreme has to happen. One of the most important processes is expansion. When gas expands, it cools. This happens because the energy of the particles is spread over a larger volume. The particles move apart, collide less often, and lose kinetic energy. This is exactly what happens in the Boomerang Nebula. The gas is expanding so rapidly that it cools faster than it can absorb energy from the surrounding universe. Another process is isolation. If an object is completely isolated from external heat sources, it will continue to lose energy over time. In deep space, far from stars, this isolation allows temperatures to drop to extremely low levels. However, perfect isolation is almost impossible. Even in the emptiest regions of space, the cosmic microwave background still provides a small amount of energy. That is why most objects cannot cool below that temperature. But under rare conditions, like rapid expansion, even that limit can be temporarily broken. There's also a concept known as thermal equilibrium. This is the state where an object is neither gaining nor losing energy. It has reached a balance with its surroundings. Most objects in space eventually reach equilibrium with the cosmic microwave background. That is why so many regions of the universe settle at around 2.7 Kelvin. To go colder, an object must lose energy faster than it gains it, and that requires very specific conditions. Another important factor is density. In dense environments, particles collide frequently. These collisions transfer energy and prevent the system from cooling too much. But in very low-density environments, like the outer regions of nebulae, particles rarely collide. This allows them to lose energy more easily and reach lower temperatures. This is why the Boomerang Nebula, with its expanding and thinning gas, can achieve such extreme cold. As the gas spreads out, it becomes less dense. With fewer collisions, there is less energy exchange, and the temperature drops even further. There is also a deeper layer to this story. At extremely low temperatures, classical physics begins to give way to quantum mechanics. At normal temperatures, we can describe the motion of particles using classical laws. But as temperature decreases, quantum effects become more important. Particles begin to behave in ways that defy our everyday understanding. They can exist in multiple states at once. They can tunnel through barriers. They can behave like waves instead of particles. These effects are usually hidden at higher temperatures. But as motion slows down, they become more visible. This is why ultra-cold experiments on Earth are so important. They allow scientists to study quantum behavior in ways that would otherwise be impossible. In the coldest regions of space, similar effects may also occur naturally. Although we cannot directly observe them in detail, the conditions suggest that quantum phenomena could play a role in how matter behaves at such low temperatures. All of this leads to an important realization. Extreme cold is not just about being far from heat. It is about how energy is distributed, transferred, and lost. It is about the balance between radiation, expansion, and isolation. And it is about the fundamental laws that govern how matter behaves at its lowest energy states. The colder we go, the more we uncover about the hidden structure of reality. And yet, even with all this knowledge, one question remains. Have we truly reached the limits of cold in the universe? Or are there still deeper, colder states waiting to be discovered? That is what we will explore next. The future of cold in the universe. When we talk about the coldest places in the universe, we are usually describing what exists right now. But the universe is not static. It is constantly evolving. And as it evolves, its temperature is changing as well. In fact, the universe has been cooling ever since the moment it was born. Nearly 13.8 billion years ago, the universe began in an event we call the Big Bang. At that time, everything was incredibly hot and dense. Temperatures were so extreme that atoms could not even exist. But as the universe expanded, it began to cool. Over time, particles slowed down. Atoms formed, stars and galaxies emerged, and the universe continued to lose heat. Today, the average temperature of the universe is set by the cosmic microwave background, about 2.7 Kelvin. But this is only a snapshot in time. As the universe continues to expand, this temperature will keep decreasing. In the far future, the universe will become even colder than it is today. Much colder. One day, billions, and eventually trillions of years from now, most of the stars in the universe will have burned out. Without stars, there will be very little energy left to heat anything. Galaxies will drift farther apart. The light from distant objects will stretch and fade, and the universe will approach a state where almost no energy remains. This is known as the heat death of the universe. Despite its name, it is actually a state of extreme cold. In this future universe, temperatures will drop closer and closer to absolute zero. Not because something is actively cooling the universe, but because there is simply no energy left to keep anything warm. Everything will reach a state of near complete equilibrium. No significant heat differences. No active processes. No motion beyond the smallest quantum fluctuations. In this sense, the coldest place in the universe may not be a location at all. It may be a time, a future state where the entire universe becomes uniformly cold. Even objects that are currently warm, like stars, planets, and galaxies, will eventually cool down. White dwarfs, the remnants of dead stars, will slowly lose their heat over billions of years. Neutron stars will cool. Even black holes, through Hawking radiation, will eventually evaporate over unimaginable timescales. When that happens, the universe will be left with only faint radiation and scattered particles. Everything will be cold, almost motionless, almost silent. But even in this extreme future, absolute zero may still never be reached. Quantum mechanics suggests that there is always some minimal level of activity, tiny fluctuations that prevent complete stillness. So even at the end of the universe, there will still be a trace of motion. A faint reminder that absolute zero is a limit that can be approached, but never fully reached. This idea changes how we think about temperature. Cold is not just a condition, it is a direction, a journey toward lower and lower energy, a path that the universe itself is following over time. And along that path, we see snapshots of what is possible. Places like the Boomerang Nebula show us that extreme cold can exist even now. Laboratories on Earth show us that we can push temperatures even further under controlled conditions. But the ultimate destination of this journey lies far in the future, a universe where almost all energy has been used, dispersed, or lost, a universe that has reached its final, quiet state. And in that distant future, the concept of temperature itself may lose its meaning, because when everything is equally cold, there is no longer anything to compare, no gradients, no flow of energy, just a vast, silent, frozen cosmos. And that leads to a profound realization. The coldest place in the universe may not be something we can travel to. It may be something the entire universe is slowly becoming. Can humans reach extreme cold? The coldest places in the universe are far beyond anything humans can naturally experience. Even the harshest environments on Earth, like Antarctica, are nowhere near the extremes found in space. But this raises an interesting question. Could humans ever reach, survive, or even use such extreme cold? The short answer is no, at least not directly. Human bodies are designed to function within a very narrow temperature range. A drop of just a few degrees below normal body temperature can lead to hypothermia. At extreme cold, cells begin to freeze, tissues are damaged, and biological processes shut down. In space, without protection, a human would lose heat rapidly. Within seconds, exposure to vacuum and extreme cold would become life-threatening. But while we cannot survive these environments, we have found ways to interact with extreme cold using technology. One of the most important examples is in space exploration. Space itself is already extremely cold, especially in shadowed regions far from the sun. Spacecraft and satellites must be designed to operate under these conditions. Engineers use insulation, reflective materials, and heating systems to maintain stable temperatures inside spacecraft. Ironically, in space, the challenge is not only staying warm, but also avoiding overheating when exposed to direct sunlight. This delicate balance shows how complex temperature management can be in extreme environments. Humans have also learned how to create ultra-cold conditions here on Earth. In laboratories, scientists use advanced cooling techniques to reach temperatures fractions of a degree above absolute zero. These experiments allow us to study quantum behavior and create exotic states of matter. While humans cannot physically experience these temperatures, we can observe and manipulate systems that exist within them. Another fascinating application of extreme cold is cryogenics. Cryogenics involves preserving biological material at very low temperatures. Cells, tissues, and even entire organisms can be frozen and stored for long periods of time. This is already used in medicine, for example, in preserving blood, sperm, and embryos. There's also a more speculative idea known as cryonics, the concept of preserving human bodies after death in the hope that future technology might revive them. However, this remains highly controversial and unproven. Freezing complex biological systems without damage is extremely difficult. Ice crystals can form inside cells, causing irreversible harm. So, while the idea is fascinating, it is far from being a practical reality. Extreme cold also plays a role in advanced technology. Superconductors, which we discussed earlier, require very low temperatures to function. These materials are used in powerful magnets, medical imaging devices, and experimental technologies. By harnessing cold, we are able to achieve things that would be impossible at normal temperatures. Even in everyday life, cold is essential. Refrigeration, air conditioning, and food preservation all rely on controlling temperature. But the deeper we go into extreme cold, the more we enter a world that is no longer familiar. A world where physics behaves differently. A world where matter can exist in strange and unexpected states. And while humans may never directly explore the coldest regions of the universe, we are still connected to them. Through science, through technology, through curiosity. We send instruments into space. We build telescopes to observe distant nebulae. We recreate extreme conditions in laboratories. And in doing so, we extend our reach far beyond the limits of our own bodies. Perhaps one day, future technologies will allow us to explore these environments more directly, or even harness their properties in ways we cannot yet imagine. But for now, extreme cold remains a frontier, a boundary between what we can experience and what we can only study from afar. And that boundary reminds us of something important. The universe is not built for us, but it is open to our exploration. The coldest place ever created, while the universe contains incredibly cold regions like the Boomerang Nebula, something surprising has happened here on Earth. Humans have managed to create temperatures even colder than anything naturally found in space. This may seem impossible at first. How could a small planet orbiting an ordinary star produce conditions colder than the vast emptiness of the universe? The answer lies in precision, control, and advanced physics. In laboratories, scientists have developed techniques to cool matter to extreme levels, not just cold, but almost perfectly still. One of the most important methods used is called laser cooling. This technique uses carefully tuned laser beams to slow down atoms. At first, this sounds strange. How can light, which carries energy, actually cool something down? The key is in how the light interacts with atoms. When atoms move, they can absorb photons from lasers that are tuned to specific frequencies. Each time an atom absorbs and re-emits a photon, it loses a tiny bit of its momentum. Over time, this process slows the atoms down, and as their motion decreases, so does their temperature. Using this method, scientists can cool atoms to temperatures just millionths of a degree above absolute zero. But they didn't stop there. To go even colder, scientists developed techniques like evaporative cooling. In this process, the most energetic atoms are removed from a system. What remains are atoms with lower average energy, meaning a lower temperature. By combining multiple cooling techniques, researchers have achieved temperatures in the range of nanokelvin. That is billionths of a degree above absolute zero. At these temperatures, something remarkable happens. Atoms begin to lose their individuality. They merge into a single quantum state known as a Bose-Einstein condensate. In this state, matter behaves more like a single wave than a collection of particles. This is one of the closest things we have ever seen to absolute zero in a real physical system. In fact, in some experiments, scientists have cooled atoms to temperatures as low as 0.00000000001 Kelvin. That is far colder than the Boomerang Nebula, far colder than interstellar space, colder than almost anything we know in the universe. So in a surprising twist, the coldest place ever created is not in deep space. It is inside a laboratory on Earth. But these conditions are extremely fragile. They require precise equipment, vacuum chambers, and careful isolation. Even the slightest disturbance can raise the temperature. These ultra-cold systems exist only for short periods of time, under tightly controlled conditions. Still, they have opened a new window into physics. By studying matter at these temperatures, scientists can explore quantum behavior in ways that are impossible under normal conditions. They can observe how atoms interact, how quantum states form, and how the fundamental rules of the universe operate at the lowest energy levels. These experiments are not just about breaking records. They are about understanding reality at its most basic level. And they may lead to new technologies in the future. Quantum computing, ultra-precise sensors, and new materials could all emerge from research into ultra-cold systems. This also raises an interesting philosophical question. If humans can create conditions colder than anything naturally occurring in the universe, what does that say about our place within it? It shows that we are not just passive observers. We are participants. We can manipulate nature. We can push the boundaries of what is possible, even in something as extreme as temperature. But despite these achievements, one thing remains true. Absolute zero itself has never been reached. And according to the laws of physics, it may never be. No matter how advanced our technology becomes, there will always be a limit, a boundary we can approach, but never fully cross. And that boundary, absolute zero, remains one of the most fascinating limits in all of science, because it represents the point where motion nearly stops, where energy reaches its minimum, where the universe itself seems to pause, and yet never completely. The edge of cold. At the beginning of this journey, the idea seemed simple. Find the coldest place in the universe. But as we've seen, the answer is far more complex. Cold is not just a number. It is not just a location. It is a story. A story about energy, motion, and the limits of reality itself. We discovered places like the Boomerang Nebula, where nature pushes temperature below the background of the universe. We explored regions of space where heat barely exists. We saw how matter behaves differently as it approaches absolute zero. And then, unexpectedly, we came back to Earth, where humans have created temperatures colder than anything naturally found in space. But even with all of this, one truth remains. Absolute zero has never been reached. It stands as a boundary, a limit written into the laws of physics, a point where motion would stop completely, but never quite does. And maybe that's what makes this story so fascinating. Because the coldest place in the universe is not just something we are searching for. It is something we are approaching, slowly, step by step. Whether through expanding nebulae, dying stars, or advanced laboratories, the universe and humanity are both moving in the same direction, toward lower energy, toward stillness, toward the edge of what is physically possible. And yet, no matter how close we get, there is always something beyond. A colder state, a deeper limit, a question that remains unanswered. So maybe the real mystery is not where the coldest place is, but how close we can ever get to it. Because at the very edge of cold, we are not just discovering the universe. We are discovering its limits, what cold reveals about the universe. By now, the idea of the coldest place in the universe has taken us far beyond a simple answer. Because extreme cold is not just a condition, it is a tool, a way to understand the deepest laws of reality. When scientists study heat, they are really studying motion and energy. But when they study cold, they are studying what happens when motion nearly disappears. And that's where things become truly powerful. At very low temperatures, systems become simpler. Noise disappears. Random motion fades away. And what remains are the fundamental rules that usually stay hidden. This is why physicists are so interested in ultra-cold environments. Because cold strips the universe down to its essentials. It removes the chaos and reveals the structure underneath. For example, in normal conditions, particles are constantly colliding and interacting. This makes systems complicated and difficult to predict. But at extremely low temperatures, these interactions slow down. Particles begin to behave in more organized ways. Patterns emerge, and suddenly, phenomena that were invisible before become clear. This is how scientists discovered things like superconductivity and superfluidity. These effects are not rare. They are always present. But at higher temperatures, they are masked by thermal motion. Cold doesn't create these phenomena. It reveals them. In this sense, cold acts like a lens, a way of seeing reality more clearly. Another important insight comes from the relationship between temperature and time. At lower temperatures, processes slow down. Chemical reactions take longer. Molecular motion decreases. In extreme cases, systems can appear almost frozen in time. This has profound implications. It suggests that temperature is not just about energy, but also about how fast things happen. In the coldest regions of space, time itself seems to stretch. Not in the relativistic sense, but in a practical one. Events occur so slowly that change becomes almost imperceptible. A cloud of gas can remain stable for millions of years. A molecule can drift through space without interacting with anything. Cold preserves. Cold stabilizes. Cold extends existence. This is one reason why scientists believe that some of the oldest molecules in the universe are found in its coldest regions. These molecules have survived since the early days of the cosmos, protected by the low temperatures that prevent reactions from destroying them. Cold, in a way, acts like a cosmic archive, a place where history is stored. But cold also has limits. As we approach absolute zero, we encounter one of the most fundamental principles in physics, the third law of thermodynamics. This law states that it is impossible to reach absolute zero through any finite process. No matter how much energy we remove, there will always be some residual motion, some remaining energy. This is not a limitation of technology. It is a limitation of nature itself. And it tells us something profound. There are boundaries in the universe that cannot be crossed, only approached. This idea appears in many areas of physics. The speed of light, the uncertainty principle, and here, absolute zero. These limits define the structure of reality. They shape what is possible and what is not. And they remind us that the universe is not infinite in its behavior. It has rules, deep, unbreakable rules. Another fascinating aspect of cold is how it connects different areas of science, from cosmology to quantum physics, from astrophysics to condensed matter. The study of extreme cold brings all these fields together, because at low temperatures, the boundaries between them begin to blur. The behavior of atoms in a lab can reflect the behavior of matter in deep space. Quantum effects observed on Earth can mirror processes happening in distant nebulae. This unity is one of the most beautiful aspects of science. It shows that the same laws apply everywhere, from the smallest particles to the largest structures in the universe. And cold is one of the keys that allows us to see that connection. As we continue to explore extreme temperatures, we are not just learning about cold places. We are learning about the universe itself, its origins, its structure, its limits, and perhaps even its future. Because in the end, the study of cold is not just about temperature. It is about understanding what happens when energy fades, and what remains when almost everything else disappears.